Recording in progress.
Hi, everyone. So we're going to be looking at our next objective, which is going to be the periodic table. We're going to be learning about what are the features of the periodic table, and as well as learning about the history of the periodic table, right? So as this objective states, we are to explain the basis for the arrangement of the elements in the periodic table, mention the historical development of the periodic table, for example, contributions from Mendeleev, and see how the classification based on atomic number is now done, atomic structure, and how we have periods and groups. So I have a little historical background here for the periodic table. So Dmitry Mendeleev was the first person that actually published a periodic table, and he placed the elements in a periodic table according to their atomic masses. So what he realized was that the elements, they behave similarly after every 8 elements. Then the 9th one would behave just like the first one. So he realized that there was some pattern in the periodic table, but his periodic table was a little bit off because he was using atomic mass instead of the atomic number. So he did not accurately group elements together by similar properties. But the other scientists who came along realized that, and then they said, instead of putting the elements in order of their mass, put them in order of their increasing atomic number. So start off with the element that has 1 proton, then you put the one that has 2 protons, then 3, then 4, then 5, and you do that. But instead of just listing out the elements, like all 103 elements like that in a line, what you do is that you realize that there are certain elements that behave similarly, so you put those elements in the same group. So there is this law called the periodic law, which says there is a periodic repetition of physical and chemical properties when elements are arranged in order of their increasing atomic number. So this is just showing you a sample of the old periodic table that Dmitry Mendeleev had made. So he did recognize that lithium, sodium, potassium, iridium, that they were in the same group because they did behave similarly, but he incorrectly placed copper in that group. So he didn't know where to put some of these elements. So to some extent it was correct, but then he had misplaced some of the elements because he was putting the elements according to their atomic mass. But today in the modern periodic table, which we now have, we put the elements in order of their increase in atomic number, as stated before. So like hydrogen is the one that has 1 proton, then we put helium. All right, then we go to lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. But what we do is that after every 8 elements, we start a new row. All right, so going across here, we call these horizontal rows, we call them periods. All right, so we realize that after every 8 elements, we should start another row. So these are called periods. These are the ones going across the horizontal rows. And then we realize that when we do that, we end up putting all the elements that behave similarly in the same vertical column, which is known as the group. So in the modern periodic table, we have groups, which are these vertical columns coming down, and that tells us how many electrons are actually on the outer shell of these elements. So if you have elements in group 1, it means they all have 1 electron on the outer shell. If you have elements in group 2, it means they all have 2 electrons on the outer shell. Then we have these elements in the middle of the periodic table. We have basically not put them in any specific group, or we call them transition metals. And then we continue the numbering over here. So this is group 3, group 4, group 5, group 6, group 7, and group 8. Sometimes we call group 8 group 0. Now the group 8 elements in this column here, they are special because they all have a full outer shell. So they have the maximum, well, helium has only 2 electrons on its outer shell, but the others in group 8 have 8 electrons on their outer shell. So they are extremely stable. They don't bond with any of the other elements because they already have a very stable configuration. But you're going to learn that these other elements from group 1 to group 7, they are not as stable as group 8, and they want to look like group 8. That is why they will either lose or gain or share electrons in order to achieve a configuration similar to that of group 8. So we have our group 1 elements, which are called alkali metals. We have our group 2 elements, which are called alkaline earth metals. As we said, these in the middle are our transition metals. We have group 3, which has boron and aluminum, that you should remember. Group 4, which has carbon and silicon, that you should remember. Group 5 has nitrogen, phosphorus, you should know. Group 6 has oxygen and sulfur. And group 7 has fluorine, chlorine, bromine, iodine, and astatine. All right, so you are expected to know the first 20 elements of the periodic table, right? You should know what groups they are in and what periods they are in. So now, as we said, the period is the horizontal row coming across. So we start off with period 1. So these elements up here, which are hydrogen and helium, they have only one shell. So the period tells you how many shells the atoms have in total. Then next we come to period 2. So all these elements going across in this row here that belong to period 2, they all have 2 shells in total. Then you have period 3. Every element in this period has 3 shells in total. And then it continues down to period 4, etc., etc. So essentially what it allows us to do when we learn how the elements are arranged in the periodic table, it means that if we see an element that we have never met before, for example, let's just look at this. So let's look at this element. We have never really done any work with this element before, selenium. We just see it there. But we can actually tell a lot about selenium by looking at its position. We can see that it is in period 4. So that means that selenium has to have 4 shells. So we know that selenium has 4 shells. That much we know. The other thing we know about it is that it is in group 6. The fact that it is in group 6, it means that it has 6 electrons on the last shell. All right. So that allows us to basically be able to predict many things about selenium. Just remember that the last shell is also known as the valence shell. All right. So that tells us a lot about selenium, because if selenium is in period 4, it must have 4 shells. The first shell has 2. The second can hold up to 8. The third can hold up to 18. But for your purposes, we will, well, in this case, it actually does have 18. But most times we say that the third shell can hold 8 and the last one has 6 because it is in group 6. So this would be the configuration of selenium. All right, so normally they don't give you these big elements though, but as we can see, we were able to predict these because of just looking at the position of where selenium is. All right, so let's look at another one that you're more likely to get. So for example, phosphorus. Without us having to do much work, we can look at where it is located. So phosphorus is located in period 3, right? So let me just bring it across period 3. So it means that phosphorus has 3 shells, all right? So it has 1, 2, 3 shells in total, all right? Because it is in period 3, all right? Next, we see it is in group 5, so it means the last shell must have 5 electrons. So if we will fill it in now, we see the first shell has to have 2, the second would have a maximum of 8, and the last has 5. So we now know that the electronic configuration of phosphorus is 2, 8, 5, just by looking at where it is located in the periodic table. All right, so the characteristics of the modern periodic table is that in the modern periodic table, the elements, which so far we have 109 elements that we have discovered, and we have made some artificial elements as well. Well, we have made some elements as well. So maybe that's why they have the 118 here. Of all the elements that have been discovered, they have been arranged in order of their increasing atomic number. That's what we use for the modern periodic table. We no longer use the atomic masses. So the groups are the vertical columns shown in the periodic table. Those are called groups or families or simply columns. And there are 9 groups, right? And then it didn't say here, but remember the periods are the horizontal rows. So let me just write that here. So the periods are the horizontal rows and they tell the number of shells or energy levels of the elements, all right, as we saw before. Okay, so just to remind you, the elements are placed in vertical groups if they have the same number of electrons on the outer shell, which is also called the valence shell. The group number tells the number of electrons on the valence shell. Okay, so there are some special names you are to know. The elements in group 1 are called the alkali metals. Those in group 2 are called the alkaline earth metals. Those in group 7 are known as the halogens, and those in group 8 are known as the noble gases. So all elements that belong to the same group will do the same reactions because they have the same number of outer electrons. So it is the number of your electrons on your outer shell that really dictates how you are going to behave. So if you are in the same group, all the elements in the same group can participate in the same reactions. So all the elements in group 1 can participate in the same set of reactions. The only difference is that they will do it at different speeds. So that's stated here. However, the speed at which the elements react will be different because the size of the elements increase as we go down the group. So remember, in the same group, all the elements can do the same reaction, but they will do them at different speeds. And we will learn more about what the reactions are that can be done by group 2 elements and group 7 elements in our next session. So again, here we have that the periods are the horizontal rows that tell how many electron shells are present in the atom. An atom in period 3 has 3 shells. An atom in period 4 has 4 shells. And as we go across the period, we will notice that the elements change from being metallic to being non-metallic. All right, so this is just showing you again the families or the groups going down the vertical columns, right, that we have, and then going across, we have the periods. So period 1, period 2, period 3, 4 going down, which tells us the number of shells. So we should now be able to tell the electronic configuration of unknown elements on the periodic table, or in the periodic table, sorry, based on their location. All right. So let us look now at this excerpt of a periodic table that we have here. So we have, well, basically, they have not labeled the groups for us. We would have to put in the period. So we know that above sodium, all right, or we should know at least that sodium belongs to period 3 so that we can navigate or orient ourselves. So sodium is in period 3. So you should remember the ones in period 3. So that means that the one beneath it would be period 4, this row coming across here, and this would be period 5, right? This is group 1, group 2, group 3, 4, 5, 6, 7, 8. All right, so based on this periodic table here, we have some elements that were not identified, but we could tell a lot about the elements just by looking at where they are. For example, X, element X, we know that it is in period 5 and it is in group 1. The fact that it is in group 1 means element X is a metal, because if you have 1 electron on the outer shell, you are a metal, and it will behave similarly to how sodium and potassium behaves, because it is a metal as well. Now, coming over here, we have element Z. Now, element Z is in period 3, so we can know that element Z, even without knowing exactly what it is, we know element Z has 3 shells. All right, so 1, 2, 3, and we can see that because it is in group 6, the last shell has 6. So we can see immediately that this element Z must have 16 electrons, and it should have a configuration of 2, 8, 6 just by looking at its position. We can also tell that element Z is a non-metal, because if you have more than 4 electrons on your outer shell, you are a non-metal. So we can see just by the positions of where an element is in the periodic table, we can tell what it is. We could also talk about element Q. Element Q is in group 2. So element Q would be in group 2, right? And it is in period 4. So it has 4 shells and it has 2 electrons on the outer shell. So it will behave just like other group 2 elements like magnesium. right? So I want us to look at what are some of the trends in the size of the atoms as we go across the period, as we go down the group. So the size of the atoms is known as the atomic radius. So this is very important because when we look at the reactivity of the elements, we have to remember what happens with the atomic radius. Now, as you are going down a group, you will observe that the elements get larger and larger. So the atomic radius increases as you go down a group, right? So any element that is lower down is bigger in size than the one above it. That's what happens going down all the groups of the periodic table. But there's something else that happens. As we go across the periodic table from left to right, we observe that the atoms get smaller in size. So for example, if we're in period 3, let's look at period 3 with sodium. Sodium is bigger than magnesium. Magnesium is bigger than aluminum. Aluminum is bigger than silicon. And it continues all the way across. So when you are going across a period, the atoms are getting smaller in size. And this is because we are adding protons to the nucleus as we go across. We're adding a proton as we go across, and the outer shell is being pulled closer and closer because we're adding more protons to the nucleus. So the nucleus is getting stronger. All right. So remember that the size of the atoms decrease as we go across a period, but the sizes of the atoms increase as we go down a group. So with that being said, we will definitely see certain trends if we are looking at a group of metals. So for example, if you're looking at, for example, group 2, right? So group 2 elements would be, we would start off with beryllium, then you have magnesium, then you have calcium, barium, then you have strontium. All right, my apologies. So it's calcium, strontium, then barium. All right, so in these elements, as we are going down the group, right, of metals, we are going to observe that the metals are getting bigger and bigger as we go down the group. All right, so as it concerns metals, metals are trying to lose electrons, right? So going down a group, and we're talking about metals. So going down a group of metals, the size of the atoms increase. And this means that the outer or the valence electrons move further away from the nucleus. So the valence electrons move further away from the nucleus as we go down the group. This causes an increase in the reactivity of metals. As we go down the group. And what we mean is that the metals lose their electrons more easily. So everybody in the group has the same number of electrons to lose. But as you get bigger and bigger in size, you lose the electrons more easily, and that makes you more reactive. So let's go over it again. So going down a group of metals, the size of the atoms increase, and this means that the valence electrons move further away from the nucleus. This causes an increase in the reactivity of metals as we go down the group, as the metals lose electrons more easily. So if we had, let's go back to this. So everybody in group 2 has 2 electrons to lose, okay? Now, as we go down the group, we will see that the atoms are getting larger. So these 2 electrons are going further away from the nucleus. It is the nucleus that actually holds the electrons in, right? So when the electrons go far away from the nucleus doesn't have that strong pull on the electrons to keep it inside of the atom. So these electrons down here it's easier for them to be lost because they are far away from the nucleus. So they're not feeling such a strong pull from the nucleus as would be these up here, which are very small. For example, beryllium is a very small atom. The two electrons are very close to the nucleus and are held very tightly. So it's very difficult for beryllium to lose its two electrons. That means that beryllium is not very reactive. But barium, which is much larger, it's much easier for barium to lose its two electrons. And so barium is a much more reactive metal than beryllium. So going down a group of metals, we will definitely see the metals become more reactive. Now, for nonmetals, now the story changes. For nonmetals, the size of the atoms still increases as we go down, because as we are going down, we are adding more and more shells. So yes, the atoms get bigger as we go down, but nonmetals are different. Nonmetals are not trying to lose electrons, they're trying to gain electrons. And it's better for a nonmetal to be small, to have a small atomic radius, so it can attract electrons more easily. All right. So if a nonmetal is large, like for example, astatine, it is so large that this outer shell is far from the nucleus. It's the nucleus that has to attract the electron. So when the outer shell is far from the nucleus, it's difficult for that electron to be attracted. But when the nonmetal is very small, it's very easy for the nucleus to pull an electron onto that outer shell. So we find that when it comes to nonmetals, they get less and less reactive as they get bigger, as you go down the group, right? So the more reactive nonmetals are smaller to the top, and the less reactive ones are larger to the bottom. But for metals, it's the opposite. The metals to the top are not very reactive, and the metals to the bottom are very reactive. So the trends in a group depends on if you're looking at a group of metals, or is it actually looking at a group of nonmetals. So for nonmetals, right, they become less reactive as you go down the group. And this is because as the atoms get larger, it becomes more difficult to attract electrons to the outer shell. So it becomes more difficult to attract electrons to the valence shell. So it is better for the nonmetal to be small than for it to be large, because it's trying to attract electrons, it's trying to gain electrons, right? So remember, for the nonmetals, they become less reactive as you go down the group. As they get larger, it's more difficult for them to pull electrons in, which is the opposite of what we saw for the metals. And then as it concerns when we go across a period. So what are some of the things we notice as we go across a period? Here we have elements that are found in period 2. We know that this is period 2 because all the elements have 2 shells. If you look at it, every element in this period has 2 shells. We can definitely see that the atoms are getting smaller as we go across the period. And that is because the nucleus is getting an extra proton as we go across. So lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, fluorine has 9, neon has 10 protons in the nucleus. So you are adding protons as you go across the period, and the electrons are still all being added to the second shell. So what is happening is that the nucleus is getting stronger and stronger, and it's pulling that outer shell, that second shell, closer and closer, and hence the reason why the atoms are getting smaller and smaller as you go across the period. So we can definitely see going across the period that there is a decrease in the atomic radius, all right? So we can see that as we go across the period. And other things we notice with the period when we go across, even though they all have the same number of shells, the elements are different. because these elements here, lithium and beryllium, they are actually metallic, they are metals. Boron is like in the middle. So boron is something called a metalloid. And these other elements here are non-metals. So we actually notice that the elements are changing as you go across a period. So as you move from left to right, the elements change from being metallic to being non-metallic. That's what happens across the period. Okay, so these over here will behave as metals, meaning they would want to lose electrons to be stable. The metalloids are in between. They behave like in some ways they behave like metals, in some ways they behave like non-metals. The non-metals now have 4 or more outer electrons, and they want to gain electrons or share to be stable. So you can definitely see going across the period that the elements are going to change in your behavior because you're changing from metallic to non-metallic. And also in the period, if we're talking about the metals alone, if we look at just the 2 metals alone going across the period, they become less reactive. All right, if I'm just looking at the metals alone, because in fact, lithium and beryllium are metals. Lithium has 1 electron on its outer shell, beryllium has 2. It is easier to lose 1 electron than it is to lose 2. So lithium is a more reactive metal than beryllium because lithium has less electrons to lose. So going across the period, the metals become less reactive. But if we look at what's happening with the non-metals now, in terms of the non-metals now, they become more reactive. So fluorine is more reactive than oxygen. Oxygen is more reactive than nitrogen. Nitrogen is more reactive than carbon. And why are they becoming more reactive as non-metals? All right, that's because they have less electrons to gain. So strange things are happening as you go across the period. So the metals become less reactive, the non-metals become more reactive, right? Because let's see, carbon has to gain 4 electrons. That's very difficult to do. To gain 4 electrons, that would mean that you have to use up a lot of energy. Nitrogen just needs to gain 3 more. All right. So remember the group numbers. The group numbers tell us the number of outer electrons. So carbon is in group 4, nitrogen is in group 5, then group 6, group 7, and then we have group 8. Okay, now everybody wants to get 8 electrons on their outer shell. So if you're in group 7, you just need 1 more additional electron to get to 8. That's easier for you to gain than if you're in group 6 and you have to gain 2 more. If you're in group 5, you have to gain 3, and if you're in group 4, you have to gain 4. So the more electrons you have to gain as a non-metal is the less reactive you are. If you have less electrons to gain, that makes you more reactive. So going across the non-metals in the period, we see that they become more reactive, but when we look at the metals, we see that they become less reactive. All right, so that concludes our session on the features of the modern periodic table. In the next session, we're going to be talking about the reactions of group 2, the reactions of group 7, and we'll go again and look at the trends across the periods.